Preparing for an AI DevOps engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How is AI DevOps different from traditional DevOps and MLOps? Traditional DevOps optimizes software delivery, while AI DevOps also manages data, models, prompts, embeddings, and feedback loops. I treat the model as a versioned deployable artifact, but I also version datasets, evaluation reports, feature definitions, and inference configurations. The pipeline must test accuracy, latency, safety, and reproducibility, not just unit tests. The biggest shift is operationalizing uncertainty. Models degrade, drift, and require continuous monitoring in production. While answering, focus on how AI DevOps extends DevOps with model lifecycle, data version control, evaluation gates, observability, drift handling, and continuous feedback from production systems. Question 2. What would a production-ready CI/CD pipeline for an AI model include? A production AI CI/CD pipeline starts when code, data, or model configuration changes. I run linting, unit tests, data validation, training or fine-tuning, model evaluation, security scans, image build, and deployment promotion. Unlike normal CI/CD, gates include quality metrics such as F1, hallucination rate, bias checks, and latency. I keep artifacts in a registry and promote the same artifact across environments, which avoids retraining surprises. Make sure to cover pipeline stages, artifact promotion, automated testing beyond code, model registry integration, environment parity, approval gates, and quality metrics such as accuracy, latency, fairness, and safety. Question 3. How do you ensure reproducibility in AI training and deployment pipelines? Reproducibility means I can rebuild the same model behavior from known inputs. I pin code commits, package versions, container images, training data snapshots, random seeds, hyperparameters, and infrastructure configuration. I also log evaluation datasets and metrics in an experiment tracker. For LLM systems, I version props, retrieval indexes, embedding models, and generation parameters. Perfect bit-for-bit reproducibility is sometimes hard on GPUs, so I define acceptable variants. In your answer, talk about deterministic builds, pin dependencies, dataset snapshots, random seeds, experiment tracking, container images, prompt version control for LLMs, and the limits of GPU determinism. Question 4. How would you deploy a machine learning model on Kubernetes for production use? First, I package the model server in a container with explicit runtime dependencies and health endpoints. On Kubernetes, I define resource requests, GPU limits if needed, readiness probes, autoscaling, secrets, and network policies. I usually serve through tools like Kserve, Seldon, Rayserve, or a custom fast API service. For production, I add canary rollout, model registry integration, observability, and rollback to the last known good version. Be sure to mention containerization, Kubernetes resources, GPU scheduling, readiness probes, autoscaling, service mesh or ingress, model registry integration, and safe rollout patterns. Question 5. What metrics would you monitor for an AI inference service in production? Monitoring an AI service has 2 layers, system health and model quality. I track infrastructure metrics like CPU, GPU, memory, request rate, errors, and P95 latency. Then I monitor prediction distributions, input schema changes, confidence scores, drift, fairness metrics, and business KPIs. For LLMs, I add hallucination rate, refusal rate, token usage, retrieval hit rate, and user feedback. Alerts should map to runbooks, not just dashboards. While answering, cover both infrastructure and model observability, including latency, errors, throughput, drift, prediction distribution, data quality, business KPIs, LLM-specific metrics, alerts, runbooks, and ownership. Question 6. What is the difference between data drift and model drift, and how would you handle them? Data drift is a change in the input distribution. Model drift is a drop in prediction quality or decision usefulness. I detect data drift using statistical tests, feature distribution comparisons, and embedding distance changes. Model drift needs labeled outcomes, delayed ground truth, shadow labels, or proxy business metrics. The fix may be retraining, recalibration, feature repair, prompt updates, or rollback. I never retrain blindly. I verify the root cause first. Make sure to distinguish input distribution changes from performance degradation. Then explain detection methods, delayed labels, proxy metrics, retraining triggers, rollback decisions, and root cause analysis. Question 7. How would you implement canary deployment and rollback for an AI model? I prefer progressive delivery because model failures are often subtle. I deploy the new model to a small traffic slice, compare latency, error rate, prediction distribution, business metrics, and safety signals against the baseline, then expand gradually. Shadow deployments are useful when I want zero user impact. Rollback should switch traffic to the previous model artifact and compatible feature pipeline. The key is testing both software behavior and model behavior. In your answer, focus on progressive delivery, canary and shadow deployments, baseline comparison, traffic shifting, rollback prerequisites, feature compatibility, guardrail metrics, and automated promotion criteria. Question 8. What is the role of a feature store in AI DevOps? A feature store prevents training serving skew by giving training and inference the same feature definitions. Offline stores support historical training datasets. Online stores serve low-latency features for real-time predictions. I use feature versioning, point-in-time correctness, ownership, lineage, and freshness checks. In DevOps terms, it becomes shared infrastructure with SLAs. Without it, teams duplicate transformation logic, create inconsistent models, and struggle to debug production predictions fast. Be sure to explain training serving skew, offline versus online features, point-in-time correctness, feature freshness, versioning, lineage, ownership, reuse across teams, and operational SLAs for production. Question 9. How would you manage prompt versioning and evaluation in an LLMOps pipeline? For LLM applications, the pipeline must treat prompts and retrieval configuration as deployable artifacts. I version system prompts, templates, tools, model parameters, embedding model, index snapshot, and evaluation datasets. Before release, I run regression tests for factuality, safety, latency, cost, and task success. I also capture human feedback and production traces. A small prompt change can behave like a code change, so it deserves review and rollback. While answering, cover prompt versioning, retrieval configuration, evaluation datasets, regression testing, safety checks, tracing, human feedback, rollout control, and why prompt changes need release discipline. Question 10. How would you use infrastructure as code for AI workloads? I use IAC to make AI infrastructure repeatable and reviewable. Terraform or Pulumi provisions clusters, node pools, GPUs, storage buckets, IAM, model registries, vector databases, and networking. Helm or Customize manages Kubernetes workloads. The important part is separating environment-specific values from reusable modules. AI workloads are expensive, so IAC also helps enforce quotas, tagging, auto-scaling, and clean teardown of temporary training environments after experiments finish. Make sure to discuss Terraform or Pulumi, Kubernetes manifests, reusable modules, environment separation, IAM, networking, GPU resources, quotas, tagging, cost controls, and teardown automation practices. Question 11. How do you manage GPU-based workloads on Kubernetes? GPU operations are mostly about scheduling, isolation, and utilization. I install the NVIDIA device plugin, use GPU-aware node pools, tates, tolerations, node selectors, and requests or limits. For inference, I consider batching, model quantization, multi-model serving, and auto-scaling based on queue length or GPU utilization. I monitor memory fragmentation, driver versions, CUDA compatibility, and failed kernels. The goal is predictable performance without wasting expensive accelerators. In your answer, talk about GPU device plugins, node pools, taints and tolerations, resource requests, batching, quantization, auto-scaling signals, CUDA compatibility, utilization, and failure monitoring. Question 12. What security concerns are unique to AI DevOps and LLMOps? AI security extends normal DevSecOps to data and model risks. I protect training data with encryption, access controls, masking, and lineage. I scan containers, dependencies, model artifacts, and notebooks. For LLMs, I test prompt injection, data leakage, unsafe tool calls, and retrieval poisoning. Secrets must stay out of prompts and logs. Compliance also needs audit trails showing who trained, approved, deployed, and queried sensitive models. Be sure to mention data protection, model artifact scanning, dependency security, access control, prompt injection, data leakage, retrieval poisoning, secrets management, audit trails, and compliance evidence. Question 13. How would you operate and monitor a RAG system in production? In RAG, the model is only as good as the retrieval pipeline. I monitor document ingestion, chunking, embedding generation, index freshness, retrieval latency, and top K relevance. Deployments must version the embedding model and index together, because changing one can break semantic search. I also add access control filters so users retrieve only permitted content. Operationally, stale or poisoned indexes are as dangerous as bad model code. While answering, focus on ingestion reliability, chunking, embedding versions, index freshness, retrieval relevance, latency, access control filters, index rollback, monitoring, and RAG-specific failure modes production. Question 14. How would you respond to a production incident caused by an AI model? During an AI production incident, I first classify whether it is infrastructure, data, model, or dependency related. I check error rates, latency, recent deployments, feature freshness, upstream data jobs, and model metrics. If user impact is high, I roll back, disable the model path, or fall back to rules. After mitigation, I preserve traces and inputs for analysis. The postmortem should include monitoring gaps, not just the triggering bug. Make sure to cover triage across infrastructure, data, model, and dependencies. Mitigation options, rollback, fallbacks, trace preservation, user impact assessment, communication, and postmortem improvements actions. Question 15. How would you reduce cloud cost for AI training and inference workloads? I reduce AI cost by measuring cost per training run, cost per prediction, and GPU utilization. For training, I use spot instances, checkpointing, right-sized accelerators, distributed training only when needed, and scheduled shutdowns. For inference, I use autoscaling, batching, quantization, caching, smaller models, and request routing by complexity. Cost cuts must preserve accuracy and latency targets. The best optimization is often avoiding unnecessary model calls altogether. In your answer, talk about cost metrics, GPU utilization, spot instances, checkpointing, autoscaling, batching, quantization, caching, model selection, request routing, and accuracy latency trade-offs in production. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.